Here we are at Physics Virtual Lab, Delhi Public School, Bangalore East, Grade 12, with yet another new concept, new experiment from Section B. Experiment 7. To find the refractive index of a liquid, we are taking water using convex lens and plane mirror. Apparatus: convex lens, plane mirror, clean transparent liquid. We are taking water, an optical needle, an iron stand with base and clamp arrangement, half meter scale. The theory: this is the ray diagram which we will be using, and this is the convex lens and this is the plane mirror. This is the liquid in between, this is water. We need to find the refractive index of water. So we have two parts again in this experiment. We have in the first part we use only the lens and the plane mirror. So when we are using only the lens and the plane mirror, we find F1. F1 is the focal length of the lens, glass lens. So F1, we will be using F1. How do we determine F1? We take an object here, this is the needle, and we need to adjust the distance of this object from the lens till we get an image coinciding with the object. And when does this happen? When the object is at F, or at its focal length, which is F1. So when the object is at F1, when an object is placed at focal length, we know that the image is formed at infinity. So we have this lens and the mirror. The water is not there in the first part. So we have the rays passing through the convex lens, and if the image of this object has to be formed at infinity, then the emergent rays from this lens should be parallel to each other. After these parallel rays emerge from the lens, they meet the mirror. They meet the mirror, and they are parallel rays. So the angle of incidence is equal to 0. Angle of reflection is also equal to 0. So they retrace the path, and the image is formed next to the object here. The dotted line over here is image. It is denoted by I in this diagram. So that's the first part of the experiment where we find F1. This distance from the lens to the object will give you F1. Okay, and also there's one more point which we are using in this experiment. Our F1 is also equal to the radius of curvature of the lens. This you can derive this using lens maker's formula and taking the refractive index of glass as 3/2, which is 1.5. Then the next part of the experiment is to find F2. Okay, to find F2, we find capital F. F2 is obtained by calculation. So we find experimentally the capital F. Capital F is nothing but the combined focal length of the convex glass lens and the plano-concave water lens. So after we determine F1, we need to add water on this mirror. We are going to see all this in the procedure. So we will add water on the mirror here and then place the lens on the mirror. So when we place the lens on the mirror, we get a plano-concave water lens. and then we determine by the same method, we adjust the object such that we get the image next to the object, and when that condition is obtained, it is nothing but the focal length, capital F, of the combined lens, and the distance from the mirror to the object will give you capital F. So 1 over capital F is equal to 1 by F1 plus 1 by F2. Our goal is to find F2. So rearrange the terms and calculate F2. Now once F2 is obtained, you have another method also to obtain F2 using the lens maker's formula. Now this is the lens maker's formula, and observe this diagram here. It's the same diagram which is rotated through 90 degrees. Now we will concentrate only on the liquid lens. So it meets this radius, this surface first from the object when it's traveling, when light rays are traveling, it meets this surface. So the radius of curvature of this surface is equal to R1. Now note that this R1 is nothing but the radius of curvature of the biconvex glass lens, and whose R is equal to its F1. So we have 1 over R1 as R, which is the radius of curvature of convex lens, and you have R2, which is the R2 now of this lens. R2 is the radius of curvature of this plane mirror. R2 is the radius of curvature of plane mirror, and for a plane mirror, the radius of curvature is infinity. So when we substitute these terms, R1 as R and R2 as infinity, R2 as infinity, then this formula comes down to this, and then because 1 over infinity is equal to 0, and rearrange the terms, you get n is equal to 1 plus R by F2. Now what is n over here? N is the refractive index of the water, because this is water lens, plano-concave water lens. So n is the refractive index of the water here. So this is our aim, to find the refractive index n using convex lens and plane mirror. Now to this formula, when you calculate, you will have to apply sign conventions of R as well as F2. R will be facing to the left. Now this is your origin, origin will be at the optic center of the liquid lens. So this will be the origin, and the distance measured from the left on the left hand side will be negative, and F2 from calculation you are going to get the sign of F2. So applying the sign for R and F2, you can find out n or calculate n. Let us study the ray diagram and the apparatus simultaneously. This is the object in the ray diagram, and this is your object needle in the apparatus. This is the glass lens in the ray diagram, and corresponding to this is the convex glass lens which we are using, and this is the plane mirror denoted by this part in the ray diagram. So this is the corresponding plane mirror. In the first part of the experiment, we are not considering the liquid. We are finding only the focal length of this glass lens denoted by F1. Small letter f, subscript 1. Okay, now you are seeing 2 pointers. One is the object here, this is the object, and the other one is the image. There's actually nothing there, that's the image. Okay, so this is the object to the left and the image is to the right, and it is coinciding. The object and the image seem to coincide over there. So the image is formed just next to the object. But when I rotate the camera, right now you are seeing through the camera lens, and when we shift the lens left and right, then see what happens to the image. We are shifting the lens left and right. You see that the object and image have changed its location. So if this happens, then image is not formed next to the object. It is known as parallax. It has parallax. We need to adjust the height of the object till we get the image coinciding with the object, even when the eyes or the lens is shifted. Even if you shift the lens or eyes. Note down this reading for the focal length f1. Small letter f, subscript 1. This is the focal length of the glass lens. Post your readings in the chat box. Okay, you have the mirror there. Now we add a few drops of water. This is water. So the liquid lens, plano-concave lens, is the water lens. Okay, so we have added little bit of water and then we place the lens on this, and now the region between the mirror and the glass lens, a plano-concave water lens is formed. And next we will be finding the focal length of the combination of these two lenses. One is the water lens plus the glass lens. So the combination of the lens, what is the effective focal length of these two lenses? Okay, now again this is the object and we need to find the focal length of the combination of the two lenses, the glass lens and the water lens. One is a convex lens and the other is a plano-concave lens. So we have adjusted the tip of the object. The one which you see on the left is the object and the one which you see on the right is the image. So we will see, we will change the position of the camera. Actually you will have to shift your eyes left and right to see if there is parallax, but now you are seeing through the camera. We are moving the camera and you see that the object and the image does not break. So it means to say that the image is formed just next to the object and it has no parallax. So next we will have to measure the distance of the object from the combination of lenses. Okay, you can record the readings. This is capital F. Capital F. Post your readings in the chat box. Check your observation. F1, which is the focal length of the glass convex lens, is 9.7 centimeters, which is also the radius of curvature of the lens, and F is the focal length of the combined lenses of water as well as the glass lens, which is 16.7 centimeters. Calculations. To determine F2, F2 is the focal length of the water lens. F2 is the focal length of water lens. So we are using the formula for the combination of lenses. This is the combined focal length F, which we have determined through the experiment, and F1 also we have determined through the experiment. So we'll calculate F2 using capital F, the combined focal length and the focal length of the glass lens. So applying sign conventions for both are positive, and then we get F2 as minus 25 centimeters. This minus sign indicates that the water lens is a concave lens. Continuing with the calculations, finally to find the refractive index of water or the liquid lens, the liquid that we are using is water. It is represented by N. N stands for the refractive index of water. And we have derived this formula under theory using lens maker's formula, where N is equal to 1 plus R over F2. R is the radius of curvature for the glass lens, and F2 is the focal length of the water lens, concave, plano-concave water lens. Okay, N is the refractive index of water. Applying sign conventions, R is equal to minus 9.7 centimeters. Over here, R, this one which is towards the left, and the origin is at the optic center here. Here is the origin, and the distances left of this origin is negative, so that is why R over here is negative 9.7 centimeters. F2 is also, you saw that it is minus 25 centimeters because it is a plano-concave lens. So applying these two, again negative divided by negative, you are going to get positive. 1 plus 9.7 divided by 25. 1 plus 9.7 divided by 25, which is 1 plus 0.388, which is N equal to 1.39 is the refractive index that we have got in this experiment for water. Result: refracting index of water, we have used water, the liquid that we have used is water, was found to be 1.39. Precautions: the liquid taken should be transparent. Only few drops of liquid should be taken so that its layer is not thick. The parallax should be removed tip to tip. Pin should be kept horizontal and its tip should be above the optical center of the lens on its vertical principal axis, otherwise it will be difficult to remove the parallax. A thin lens should be used so that the distance measured from the surface is nearly equal to the distance measured from optic center. It is better to measure distance from both the surfaces and take the average. Sources of errors: the surfaces of the convex lens may not have the same radius of curvature. The plane mirror may not be horizontal. The focal length will not be accurate as the lenses have some thickness. Points to ponder: what will happen if you are given a convex lens of small focal length? What are the basic assumptions you have made in performing this experiment? Why do we have to raise the object pin upward after filling water between the lens and the mirror? How is a plumb line effective in ensuring that the rays retrace their path after refraction through the lens and the reflection from the mirror? Draw suitable diagram with principal axis at an angle to the vertical, showing the plane mirror at an angle to the horizontal. That's all for today. Remember to note down the date, complete your record, keep experimenting. Thank you.